Welcome. In this session in linear data analysis, we'll explore how to write a matrix as a series. This is a slightly unusual topic because normally when we write a matrix, we think of it as a factorization or a decomposition, that is, as a product of matrices. And there are certain specialized applications where it's useful to think of a matrix as a sum. So let's recall the SVD of a matrix. So that means we can write any matrix A as the product of an orthogonal matrix U, a diagonal matrix sigma, and an orthogonal matrix V transpose. And let's suppose that the rank of the matrix we're looking at is R. And now let's try writing this explicitly in terms of the vectors that are in these orthogonal matrices. So let's try writing sigma times V transpose. Well, that will equal the singular value matrix will be sigma 1, sigma 2, and so on until we get to sigma R. And V transpose will look like that will be V1 transpose, V2 transpose, and so on until we get to VR transpose. And let's recall that if the matrix was originally not square, that we would have, if it was not square, we might have zeros down here or zeros down here, and those wouldn't contribute to the ultimate product. And similarly, if there were non-zero singular values, those would end up multiplying and not contributing. So now, what is a way that we can write this? Well, let's put in the zeros for a few of these so that we can see what might happen. Well, when I multiply sigma 1 times V1, and then all of those are zeros, so that has to be sigma 1 times V1 transpose has to be the first row of that product matrix. Then the second one has to be 0 times V1 plus sigma 2 times V2, sigma 2 times V2 transpose, and so on. All of those will be 0, and that pattern will persist. So each one of these, if I multiply the singular value matrix by the rank R orthogonal matrix, that is sigma R VR transpose. Now, what happens when I multiply U by this? So that means that the matrix A equals U times this product that we've calculated, and that equals, so now that will be the matrix U will represent as columns, so that will be column U1, U2, and so on until we get to UR, times, and we'll repeat this, is sigma 1 V1 transpose, sigma 2 V2 transpose, and so on until we've represented all of the relevant entries. And when I do this product, what do I get? Well, I get U1 times sigma 1 V1 transpose. U1 sigma 1 V1 transpose. And let's observe that that's a matrix. That is, this matrix is, this is a row, and this is a this is a column rather, and this is a row. So a column times a row is going to be a matrix. It, it may be rectangular if U and V don't have the same size, but this will be a matrix. And then we'll add, as we continue, what we do is we take this product and add this product. So we then add U2, sigma 2, V2 transpose, and so on until we've represented all of the relevant U vectors, sigma values, and transposes of the V vectors that are present. So what we're able to do here is we're able to take any matrix, and by using the singular value decomposition, we can represent it as a sum. Now let's make a couple of observations here. We could ask, what is the rank of this matrix here? Well, that would be a rank 1 matrix, because what's happened is, if we think about this one, let's write this down separately. If we say, let's drop the subscripts for now. What is U times V transpose? Well, that has to be a matrix. So this would be U times V1. So this would be V1 times the column U. The next column would be V2 times the column U, and so on until we get to Vn times U. Sorry, that shouldn't be there. That should be there. So this, what's the rank of this? Well, this column is a scalar multiple of this one, and so on. Each of these columns are scalar multiples of each other. So the rank of U V transpose is 0 or 1. Under what conditions is it 0? Well, either the U vector is 0 or the V vector is 0. If it's coming out of the singular value decomposition, we're guaranteed that the rank is 1. And the reason is that U can't be the 0 vector because it's a column of an orthogonal matrix, and V cannot be 0 because it's also the column of an orthogonal matrix. So I can tell that UV transpose is a rank 1 matrix, and what we're saying is that any matrix of rank R can be represented as the sum of R matrices, each individual being rank 1.